That's exactly right. All right, here we go. Erythroblastic island. So we've already talked a little bit about the erythroblastic island. This kind of goes into a little bit more detail. We talked about this in chapter 1 or in chapter 3, I believe. But just a little more on it. Just make sure you know that there is a nurse cell, which is a macrophage. All right, so it is basically the center of your erythroblastic island. But what's really cool about this thing is it actually extends little cytoplasmic extensions to all of the erythroblasts. So you remember we talked about how that up here, you're going to have those, I'm going to go ahead and try to always do it the right way, pronormoblast, I think how the ruboblast is. So it's always the earliest form of the erythroblast that's right up against the macrophage. And then as they go out, away from it, they get more mature until eventually they're just erythrocytes, okay? So that sequence that we talked about Monday in class from the pronormoblast all the way down to the mature erythrocytes, okay? You're going to find these surrounding. But what's cool about it is, not only does it have extensions to the ones that are close, but even down here, it sends out cytoplasmic extensions to those cells. And the reason it's doing that is because it's essentially keeping contact, because it's kind of measuring its growth and where it's at in its maturation, because it may need other cytokines to help it to continue to grow. Does that make sense? So this nurse cell is a very important part of erythropoiesis, okay? So if you have something that happens to your body and you don't produce macrophages, monocytes, then you're going to have problems with your red cell ability also. Does that make sense? Okay? Yes, ma'am.
Did you say the further away, the more mature it is?
Yes, yes. The ones that are closer to the macrophage are more immature. So that's going to be your ruboblast, pronormoblast, whatever you guys know them, the prorubes and so forth. And then as they go away from it further out in the ring, okay, they're going to get more mature as you go down. Okay, to eventually you may even have some mature red cells that are kind of surrounding the bottom of the island. But they're getting ready to basically cessation to go out, you know, the egression. Remember we talked about egress when it leaves the bone marrow and goes into the peripheral blood. Okay? All right, questions about that? All right. So these erythroblasts, they adhere to the macrophage like we talked about. They have cytoadhesion molecules, and one of the big ones is known as fibronectin, which is just a protein that helps the erythroblast to stay stuck to that macrophage. Okay. So as the cell matures, it loses the adhesion molecules, then it detaches, and it passes through a pore in the cytoplasm, which is the egress, the egression that we talked about before. Then it enters the circulation, where once it enters the circulation, stays in the bloodstream for approximately how long? 120 days. Very good. All right. So basically, this central macrophage also has other duties. It does, not only does it produce cytokines, but it also does phagocytosis. Okay. So not only is it doing phagocytosis of the nucleus that's being expelled from the metarubocytes, also known as the orthochromic normoblast, I believe. Those cells, once they push out that nucleus, the macrophage will gobble up the nucleus. But it is also there for protection, okay, from foreign things. So things like bacteria, fungi, anything that wants to get in your bone marrow, these macrophages will also play a role in that, okay? So not only that, but it also plays a role in defective erythroblast. So let's say that a cell is in that orthochromic normoblast stage, and then for some reason it doesn't ever lose its nucleus. It just kind of sticks in there the whole time. Well, that macrophage is smart enough to know that it should already be going to the next stage, which is the retic. Okay? And if it doesn't ever get to that part, the macrophage knows that its time is up. So it must be a defective cell. It didn't ever reach true maturation. Okay? So what it'll do is it'll come in and engulf it and destroy it. Okay? And so that's one of the roles that the macrophage does also. And there's lots of things that can happen during the maturation period. The membrane could get damaged. The membrane of the cell could get damaged. The nucleus could get damaged. And so if anything like that happens, then that macrophage senses it and goes in and destroys it. Okay? So that's another role of that nurse cell. Okay? Questions about that? All right. Any questions about the erythroblastic island? Because now we're moving on. We're not talking about it anymore. We good? Does that make sense? Okay. And remember, it's in a little particular niche inside the bone marrow. Okay. And we'll be able to see some of these when we look at some bone marrow slides this week. Okay. Or next week. All right. All right, so let's talk about the membrane of the erythrocyte. The membrane of the erythrocyte is very, very important, okay? It is essential for erythrocyte development and function, all right? So, why is it essential? Well, it's essential up here in the pronormoblast. Let me ask y'all this. Is this an A or O? From normo, or is it mo? It's an O? Okay. See, I hadn't looked at it enough to remember. So pronormoblast, okay, this membrane is very important because for it to be able to mature to that erythrocyte that we're looking for to be normal down here, it has to have receptors for EPO, interleukin 3. There's 4 or 5 other ones that affect the growth and maturation to this point. So without these receptors, the cell is dysfunctional, and it'll just hang out in this stage for the rest of its life until one of the macrophages says, hey, you're not doing your job, we're going to kill you. Okay? Because that's what your body does. Your body's very efficient. Okay? Something's not doing its job, it gets replaced. Okay? And so it would destroy it. So without those receptors around the cell membrane, the cell wouldn't know what to do. It wouldn't be able to receive the cytokines to help it to mature to what we need it to get to, okay, as we go. All right? So very, very important development and function. So erythropoietin and transferrin. We hadn't talked about transferrin. Transferrin is the iron transport protein. It's the only protein okay, only iron transporter. Okay, so you already know enough about the red blood cell that it has to have iron, right? Because iron is necessary for what production? Hemoglobin. And what does iron do in hemoglobin? We haven't really talked about this that much. I'm just seeing if you guys are logical. Why is iron so important in hemoglobin? And if I don't paint it, what happens to it? It oxidizes, which is rust, right? Okay? So iron is responsible for bonding to oxygen, okay? We actually form a little bit of rust in our red blood cells in the form of iron oxide, okay? Iron, if you don't have iron, you don't carry oxygen, okay? You can still, okay, theoretically, listen to me, you can still have hemoglobin without iron. Hemoglobin is a separate protein, but iron gets bound to the hemoglobin molecule, okay? And iron is necessary for oxygen transport. It's the only way it can happen is for it to do that, okay? So transferrin is a very, very important receptor on our cells because it has to get iron into that hemoglobin for the red cells to do their job, okay? So very, very important, all right? Okay. The membrane also selectively sequesters vital components, okay? So you ever heard that old saying, or the saying in biology, it's a semi-permeable membrane, okay? What does semi-permeable mean?
Only certain can go in.
There you go. Certain things can go in and certain things can't, right? Same way with our red cell. It is a semi-permeable membrane, okay? Allows escape of metabolic waste products and then regulates metabolism. It reversibly binds and inactivating many glycolytic enzymes, okay? What's glycolytic mean? Anybody? What's glycolytic? That's exactly what it is. Breakdown of which sugar in general? That a girl. Glucose, right? So glucose is how we do, we get energy in our body, no matter what, okay? I know people are down on sugar right now. You know, everybody says, oh, you gotta have sugar-free this, and can't eat sugar, you gotta have sweeteners other than sugar, you know? But guess what? You have to have glucose. If you don't have glucose, you die, okay? So you've got to have it one way or the other. And the reason we do is because we take one glucose molecule and we get 2 ATP. Okay, it's not exactly right, but just basic it is. It's actually, we take 1 mole of glucose and get 2 moles of ATP, okay? Remember moles from our wonderful math class last semester. You know, guys taking chemistry now, you'll learn moles. So moles are very important to us, okay? Or glucose is very important to us. So what it's talking about is it's able to take byproducts, things like CO2, ATP, and those products that we have from glycolysis, which is what glycolytic means. Glycolysis is the process of breaking down glucose, okay? There's actually 2 forms. Glycolysis. I think that's how you spell it. That's right. Glycolysis, you can have aerobic, but you can also have anaerobic. Okay? This is what happens in the mitochondria, known as, let's see, it's not called, it used to be called the Krebs cycle. Now it's not called that though. Now it's called the Emden. Meyerhoff, I think. That may not be spelled exactly right. It's called the Emden-Meyerhoff pathway, is what it's called now. Okay? But my point is, we make pyruvate, and then pyruvate makes ATP through another enzymatic reaction. Anaerobic anaerobic, though, occurs in just anywhere. There's lots of places we can do it. And in this, we make lactate. And then lactate makes ATP. Okay? Now, byproduct of this is water plus CO2. Okay? The byproduct of lactate, though, is lactic acid and water. Okay? So lactic acid is a big problem when we have that. So we don't do real well with lactic acid. Some of you guys that are in shape, you could probably go work out and the next day you don't have any problem. Fat boys like me, I go work out, run, or the worst is like my dad metal detects. He's retired. So I bought him a metal detector. I actually bought me and him both one. And like they were $600 a piece. And so they're really, really good, you know, some of the top of the line metal detectors. And he is hooked on it. I mean, like he goes 2 or 3 times a week, you know, metal detecting. He has found like 80 rings. He found a ring the other day. It's worth like $3,000. It's a mason ring. Y'all, any of y'all's family in the Masons? It's a mason ring. It's a double needle mason, 32nd degree, which is highest you can go. It's got a big diamond in it. Everything. It's like $3,000. You found it 21 inches down in a hole. Yeah. So anyway, everywhere. He goes like churchyards, and he comes out here at Gadsden State all the time. When I'm at work over here, across on the East Broad campus, that big open field down toward the end of campus. He's covered it like 5 or 6 times. But my point is, I don't get to go every day like him. You know, I have to work still. So about once a month or once every 2 months, I'll go with him on a Friday or Saturday that I'm off. And like the next day, I am dying because I do this constantly, you know, because you're getting down and then digging and then you're getting back up and you're walking the whole time. So like the next day, I can't sit on the commode, you know, because the back of my legs are like sore as they can be. Why? Because of this. Because my body, fat and old and out of shape, used all of its oxygen, so it stopped doing the efficient respiration, glycolysis, and started doing the inefficient form of glycolysis. And so I started making lots of lactic acid, and the way my body gets rid of it, it just stores it in my muscles. Well, my muscles don't like it, and so it hurts, you know, so it causes pain. Your red blood cells RBCs do this. This is their main form of glycolysis. We still have to break down glucose and have energy in our red cells because they've got to live 120 days, right? So they have to have energy. They don't have a mitochondria, so they have to do it through anaerobic. Yes, ma'am?
Is that why people who have sepsis have really high lactic acid?
That's exactly what it is. That's exactly why. And that's why we do lactic acid levels on patients that we suspect have sepsis. And essentially what's happening is when you get septic, your system starts shutting down. And so they're not doing what they should do. Your body's not taking in the oxygen it should take, or it's using the oxygen up really, really fast. And so then their body converts to anaerobic respiration, which is talking about glycolysis. Okay? You guys do realize that, right? Cellular respiration is the same thing as glycolysis. It's the same term. It's just 2 different terms for the same process. Okay? So glycolysis is cellular respiration. All right? So aerobic and anaerobic, and so this is what occurs in the red cell. We're going to talk about that in just a second, but just kind of got ahead of myself a little bit. Okay? All right? The erythrocyte also plays a balance in the exchange of ions. Okay, so what's an ion? Somebody didn't pay attention to chemistry, did they? What is ions, guys? What are ions? Come on, man. An atom with a charge. That's simple. You guys ought to know that from chemistry, for sure. Ions are atoms without charge. So we have two types of ions that we can deal with in the world, and in our body especially. What are they? Huh? So, what did you say?
Cations and anions.
Cations?
Is that what it is?
What the hell's a cation? It's a cation. Your teacher called it a cation?
Yeah.
Cations are positively charged, and anions are negatively charged. Now, I got an equal sign. I know it's probably going to sound strange to y'all. But in the lab, we don't use a minus. A minus looks like a dash. Okay? So anytime you put negative, you use an equal sign or a zero. Okay? Those are negative. Those are things that we use for negative in the laboratory. Okay? An equal sign or that. Cation. A cation. I've never heard that. What teacher said that? Like your high school teacher or like your college? Surely
I
not
took it
college.
online in college, so I never heard of
Okay. It's a cation is what it's called. It's called a cation. Uh-huh. Huh?
So it's anion?
And an anon. Yeah. Or just an anon is what a lot of people, everybody I've ever heard. What does she call this one?
Anion?
An ancient?
Anion?
I love it. I love it. Where'd you go to school?
Weaver?
There you go. That explains it. Hey, no, they taught chemistry at Weaver.
I don't.
Apparently not. Apparently not. So cation and anon, okay? So positive and negative ions, okay? That's our big deal. The three that we worry about the most are sodium, potassium, and chloride, okay? Sodium and potassium are your cations, and chloride's your anion, okay? Now, bicarb is HCO3, and it's negative, I think. No. Let me think a minute. My brain just went blank. Y'all have that problem?
And what's the other?
Sodium, potassium, and chloride. So sodium. Somebody look that up for me, because I had a brain fart there for a second. Cation got me. Cation threw a monkey wrench in me.
What are we looking at?
Look up bicarb and see if it's a cation or an anion. I can't. It's a polyatomic. It's not going to be on the sheet there.
It's negative.
It's negative? Yeah, that's what I thought, but then when I wrote it up there, I thought, that's not right. And it's HCO3, right? Maybe.
Yes.
All right. And this is known as bicarb. Bicarbonate is what it actually is called, but a lot of times you'll see it referred as just bicarb, okay? Why is bicarb important to us? I'm throwing this out there to see if you guys know anything about this stuff. What does bicarb do in our body? Anybody know? But very important. It's actually one of the most important compounds in our body. pH, that's exactly right. Bicarb is a buffer. You guys know what a buffer is? Okay, so let's say that, all right, so you a Yankee, right?
I'm not a damn Yankee.
Missouri?
Yeah, she's a damn Yankee.
Missouri? You close enough. And let's just say, I'm giving you the benefit. I guess you technically are a damn Yankee.
Because she's studying.
Because you're here to stay, right? You know that's what a damn Yankee is. A Yankee's just somebody from the north that comes and visits. A damn Yankee's one that comes and lives here. You didn't know that?
You're a damn Yankee.
You a damn Yankee.
Alright.
So, wannabe southerner from Missouri here, okay? I'm gonna throw something out there, because I know I see you got like a gallon of coffee there. So do you drink, what do y'all say? Y'all drink, you drink pop? Is that what you call it? Soda,
I don't
soda,
call it.
soda. Y'all don't call it Coke?
They do. Texas, everything is good.
Everything's Coke. Well, in Alabama, everything's Coke
Okay.
too, yeah. So, but sodas, do you drink sodas?
Not really. I mean, a little bit.
Every now and then? Okay. So what if I told you a soda's pH was 3? Yeah, like eat your face off, acidic.
Yeah.
Like literally, if you put a steak in a bowl of Coke and left it for 4 days, you would not have a steak when you came back, because it would eat it, it would dissolve it, okay? So pretty rough, right? Okay, so our blood pH is 7.35 to 7.45, and that's what it needs to stay. And if it gets too much above this, okay, or below it, let's say it gets to 7.25, and let's say it gets to 7.65, you know what happens? Either way, you die. That's exactly right. You die. Okay? Because we need to have this. So if you drink a 3 pH soda, what keeps your blood from dropping down below 7.35?
Bicarbonate.
Damn Yankee.
The bicarbonate.
Bicarbonate.
Where do you get
How does it do that? Okay. Well, let's analyze bicarbonate. Okay. Bicarbonate is hydrogen plus CO3. Right? Because this is carbonate. It's a polyatomic ion, and this is hydrogen. What is the definition of pH? Percent hydrogen. So this guy is a pain in our butt, in our body. So we have to have a way of absorbing all the extra hydrogen that we ever produce or ever come in contact with. So what does this also look very similar to? Carbon dioxide, right? And we have lots of carbon dioxide in our body all the time, right? Because our muscles are always doing what we talked about before, turning glucose into pyruvate, and then pyruvate into ATP, giving off water and CO2, right? So we have it all the time. So our body is designed, this CO2 forms a bond with hydrogen, okay? Of course, it adds another oxygen, in the mix too, okay? Because we have lots of little oxygen molecules hanging around also, and we form bicarb, okay? This bicarb, being able to absorb hydrogen ions, is what gives us the ability to keep our blood pH here, okay? Now, inside our red cell, okay, the pH is probably around there. And the reason we do is because we have more carbon dioxide inside the red cell than we have anything else. Carbon dioxide, okay, so let's talk about soda again. So why is pH of soda so low? They pour battery acid in it? No, they don't. No, they don't. But what is battery acid? Battery acid is sulfuric acid. So H2SO4 is sulfuric acid. Okay? But what's in Coke that makes it so acidic?
Caffeine.
Oh,
Right?
Carbonate.
Carbonation. Okay? So when carbon dioxide is added to water, we get hang on a minute, H2CO3, which is carbonic acid. Okay? Carbonic acid is what's inside our red cells. all the time. We have lots of carbonic acid inside our red cells. So the pH of our red cells, and I was wrong, I said 6.7, I said this way, it actually is more this way, okay? It's more acidic, is what I was trying to get at. The red blood cell inside the red cell is more acidic than your plasma and your blood inside your vessels. Does that make sense? So like your plasma that's flowing around in your body, the pH is about 7.35 to 7.45, which is what we want it to be. But if we took the pH inside your red blood, inside your red blood cells, it'd be near 7.25 and maybe even lower than that because of the carbonic acid that we have. Okay? So like blowing y'all's minds back, right? Okay. So just get this though. That's the big thing. Alright, so these 3 and 4, including these are the main ions that I need you to make sure you know what's going on with. Okay? Alright, so serum or plasma, okay? Alright, what's the difference in these two? Taught you guys this last semester. What's the difference between serum and plasma? Serum's missing something. What's it missing? What is it? Starts with an F. It's protein. How did I get a serum tube? Which tubes in phlebotomy that I taught you guys make serum? SST, right? What's missing in SSTs that all the other tubes have? An anticoagulant. So what happens in a serum tube? You get coagulation, so you get a clot, right? What causes us to clot? Fibrinogen. Remember, fibrinogen is changed to fibrin, right? And your fibrin holds the clot together. So in serum, it's just like plasma with the absence of fibrinogen, right? There's no fibrinogen. Plasma has fibrinogen. This is the one that's like our normal liquid that's flowing through our blood. Okay, it has all the proteins and everything it needs. Okay? Plasma or serum, okay, have increased sodium and chloride. Okay? Okay?
Both of them?
Both of them.
Yeah, both of them. Okay? Why do you think both sodium and chloride go hand in hand with each other? Table salt. Salt in general. That's exactly right. Probably not technically table salt, because what would table salt also have in it? Iodine. Somebody said it back there. Iodine. Why do we put iodine in salt? Why do they put iodine in salt in America? Or all over the world now, just about.
I know that. I don't know.
What do you get if you don't have iodine in your body?
Isn't it Graves' disease?
Huh?
Goiter?
Goiter. That's it.
What
The
is
goiter.
goiter?
It is a form of like Graves' disease. Yes.
What is
It's
it?
a goiter. A goiter is like a big old knot. So go back in if you can. A goiter. Mhm.
Goiter.
Yeah. Goiter.
Goiter.
Yeah, goiter.
Goit.
Goiter. I'm from Alabama, damn Yankee. I talk the way I talk.
She's
Okay.
just like you're putting
It's
all
a
over.
goiter. Goiter.
Goiter.
Goiter. It's a goiter. Okay, it's a mass in your throat. How about that? And the reason it is because the thyroid gland gets enlarged. People do, if you don't have iodine, okay? Iodine is a necessary compound to make T4 and T3, which are thyroid hormones. T4, T3. Thyroxine and triiodothyronine. Okay? T4, T3. We'll talk about this later on in chemistry. You don't have to even worry about it. I'm just mentioning it because she said table salt. Most of you guys, if you go home and pick up your table salt, got iodine in it, right? Iodized salt. That's what most people use. We are in a kit where everybody's using sea salt and that pink Himalayan salt. So my theory is that eventually, if we keep doing this, you're going to see people walking around with goiters again. Goiters. Goiters.
It doesn't have
Is that it? Goiters. Is that how you say it?
Goiters.
Goiters. Goiters. Goiters.
Does pink Himalayan salt have iodine?
No,
Why?
it doesn't. Because it just doesn't have iodine. Iodine's added to just
Oh.
regular salt. I mean,
Oh.
they take regular sodium chloride and add iodine to it in the box.
And you can't use the iodized salt in the fish.
Huh?
You can't use the iodized salt in the fish.
Exactly. Yeah. It'll mess up the fish. Okay? All right. I don't know why we're talking about that, but yeah. Because we're talking about sodium and chloride. That's why. Okay? So, in serum, okay? So, let's pretend. All right? So, this is my vessel, and I've got red cells floating around in it, you know, because that's what they do all the time. Okay? And then I've got my plasma that my cells are suspended in. Okay? All right, listen to me. Sodium in the plasma is about 135 up to 145 milligrams per deciliter. Okay? That's sodium. That's your normal level. Should be there all the time. Okay? Also, there are a few potassiums floating around. Okay? And of course, you've got chlorides. Okay? Alright? So, chloride is about anywhere from about 90, I'm gonna say 95, that might be just a little bit low. 95 up to about 120. No, I think that's too high. I'm gonna say 110 milligrams per deciliter. Okay? So you notice they're pretty close to each other. Okay? But look at potassium. Potassium, 3 to 5. Oops. Milligrams per deciliter. Okay? And I think I've got that wrong. I think it's actually most places nowadays, they do millimoles per deciliter. So let's do that. Because you're dealing with an electrolyte, you're dealing with an iron, so it's going to be like moles, millimoles per deciliter. Okay? But the point is, look at it. That's your normal ranges in the plasma.
Is
And
that
the
3?
Huh?
3 to 5?
3 to 5, yeah.
Okay.
Sorry, my 3 bad.
It looked like a 2.
Sorry. 3 to 5. Okay? Get very much higher than about 7, you're dead. Yeah? Get below about 2, you're dead in potassium. Okay? Alright, potassium's a bad one. This guy kills you, you know. These two you can deal with pretty well, you know, high or low. But that one kills you because it's necessary for like muscle contractions and stuff. Hang on.
Is that why people who have low potassium have seizures?
Yes, they have lots of problems and they die a lot. Yes,
I thought I was having a heart attack when I got to the hospital. It was 2
and your potassium was low.
And I had a wreck that day.
Yeah.
Like,
Stress.
I forgot to put my car in park.
Yeah.
I couldn't.
Yeah, because you can't function.
Right.
Okay.
Is that in
ML, millimoles, like that, millimole, M-M-O-L. Okay. All right. So look, these numbers are plasma. Okay? Now, inside the RBC, okay, so if we look inside the RBC, we would see potassium of about 135 to 145 millimoles. Okay? And then sodium, it's going to be 3 to 5. Same way with your chloride, it's very low too. It's actually a little lower, it's like 2.5 to about 4.5 millimoles. Okay, so you see the difference in the two? Okay, so inside our red cell, potassium is the main goal. It has the most of the cation ions, okay? Whereas in the plasma, though, it is very low, all right? So that's important to us, okay? So, think back to phlebotomy. Remember we talked about when you have a hard time drawing the blood and you pop those red blood cells, and it's called what? Hemolysis, right? So, something we talked about, you have to do what when your sample is hemolyzed? You have to recollect it. Well, one of the reasons we have to recollect it is because instead of having 3 to 5 potassium level, we popped all those red cells and look how much potassium we dumped into the plasma. So this number may be 10. Guess what? That's not compatible with life. If your serum plasma potassium level got to 10, you'd be dead. Okay? But your instrument don't know that. It's just testing for potassium, right? But we popped all these red cells and leaked all the potassium out into our tube. Does that make sense? See? Okay? So that's the reason we have to recollect from hemolysis. Okay? Now, inside our red cell, okay, we have pumps that are called sodium, potassium pumps. Okay, so what does that mean? So a while ago we talked about how, all right? Remember how we talked about it's a semi-permeable membrane around the cell? Okay, so y'all remember from phlebotomy, we talked about this word. Talking about diffusion. Remember I was talking about diffusion? Okay. So Haley, let's say that you go to the movie theater tonight and you get a large, extra large bucket, 5-gallon bucket of popcorn, and you pour the salt box on top of it, right? And then you add butter on top of it, which also has salt in it, okay? And then you sit there and you eat every bite of it on your movie while you're watching the movie, okay? What is going to happen to your sodium level in your plasma? Huh? It's going to increase, all right? So if your sodium level increases, all right, inside your red cell, it's supposed to have low sodium, right? We said low sodium, increased potassium, right? Oops. Correct? What's going to happen to the sodium that's in your plasma? What's it going to try to do? That's exactly right, because remember what I said a long time ago? Our body likes to be efficient, but it also likes equilibrium, right? So if I've got way too much sodium here, and I've only got a little bit of sodium in here, what's my body going to naturally try to do? That's exactly right. It's going to try to push sodium into the cell. Well, if I push a bunch of sodium inside my cell, what's it going to do to the equilibrium inside the cell? It's going to say, hey, sodium's positive, potassium's positive. Can't have that many potassium ions, right? So what's it going to do? It's going to kick potassium out, and then what's going to happen to our level of potassium here? It's going to increase, okay? So when your doctors, you know, as much as I don't like doctors, once your doctor gets onto you about your sodium level, why he's getting onto you about your sodium level is it's not that he's really concerned about your sodium level as much as he is the effects it's going to have on your potassium level. Does that make sense? Okay? So that's what our membrane for our red cell does. It kind of controls that equilibrium and allows things in and out. Okay? This is nothing. Wait till chemistry. She'd be saying, I'm not going to be a damn Yankee. I'm just going to be a Yankee. I'm going back home. All right. So balance is very important. Cation, water balance, all these things have to maintain the RBC ionic composition. Okay? Questions about any of that kind of stuff? I know that's a lot, but that's just basic chemistry. Okay? Really and truly. All right? And we'll talk more about this when we get into chemistry. Just know that membrane is very, very important to us. Okay? And those three, four ions. Make sure you're familiar with those. Okay? All right? So let's talk about the cytoskeleton. So even though the red cell loses its nucleus and all that stuff at maturity, it still has its exoskeleton or cytoskeleton. So basically the cytoskeleton is very important because, all right, we talked a little bit about this the other day. There are places in our body where blood has to go that it has a hard time getting through. Okay? You have some vessels in your body, like capillaries, that blood has to pass through. Well, sometimes those capillaries, a red cell, we said, was how big? How big is a red cell? Now remember? It's a biconcave disc that is about how many micrometers across?
7 to 8.
No, I don't think so. Not that high. I think it's like 5 to 7, isn't it? 7 to 8 is too large. Is that what it says? It says 7 to 8? Well, we need to change that. 5 to 7.
I'm not lying.
Okay. Let's say 5 to 7. Hey, it really does. Crazy. All right. Okay, 7 to 8. We'll go 7 to 8. All right. Either way, let's say that from here to here is only 3 microliters. That don't work good, does it? That's got to get in there, right? Because it's got to go. So what's it got to be able to do?
Make it flexible.
Exactly. It's got to be flexible, and it's got to be able to slide through. Okay? All right. But once it ends here, what's it got to also be able to do?
Bounce back.
It's got to bounce back. Okay? It can't bounce back if the cytoskeleton is not flexible. Okay? So that is an important thing. All right? So let's say that I've got a cell that makes it through, but then when it gets back here, it stays small. What's going to happen to that cell?
It'll get eaten.
It's going to get eaten by what? And where? You're right. It's going to get eaten by macrophage. Where's that going to occur? I think you're missing one.
In the spleen.
That a girl. The spleen will knock it out. Okay? So that flexibility is very, very important for survival and circulation. If it can't be flexible and do what it needs to do, then it'll never make it through the body very long. And the spleen will remove it. Okay? All right, how we doing time-wise? We okay? Oh, yeah, we got plenty of time. We're in good shape. All right? So let's talk about the membrane composition, because this is important, because sometimes when the composition of the membrane gets messed up, the cell gets messed up, and it's not the same as it should be. All right, so I'm going to take you back to biology. How many of you had biology recently? That many. Dang. You had it recently? Okay, so this will be a review for you. For you guys, though, that haven't been here in a while, all right?
They look like little squids.
They look like what?
Little squids.
Little squids?
Yeah, that thing.
Jellyfish.
I think they were
Little squids. Okay. Got a lot. Cashin? So
And Anna.
Listen,
And
they fired our chemistry
Angie,
teacher, so
Angie,
the cheer coach
Angie.
taught me chemistry.
Cashin and engine.
Did you hear what she
The
just
cheer
said?
coach taught me
The cheer coach taught chemistry. So, did she make it okay?
She's also a bus driver.
After school. In Weaver, she might be. Probably the principal's wife too.
No, she's working.
The,
So songs.
Guidance counselor's wife. Okay? So, essentially, all membranes and most of the cells that we have in our body are a double membrane. It's a double membrane. And it works that way because most all of the cells, of course I always say most because there's always an exception, most all cells are semi-permeable membranes. So they have to have ways of going in and out. So this is a phospholipid, okay? One of these guys is known as a phospholipid. Okay, phospholipid, I think that's how you spell it. May have had an extra O, but I think that's right. Phospholipid. Phospholipids. So a phospholipid is a compound that has a phosphorus head, or a phosphate head, let's just say it that way, because it's actually a phosphate head. Okay? All right. Phosphate head is hydro, whoops, no, that's right. Hydro, I think I've got an extra R. Hydrophilic. Come on. What's hydrophilic mean? It is a water lover. Okay? Then it's got two fatty acid. Okay? Anytime you see fatty acid, your brain needs to think triglyceride. Okay? It's not a triglyceride, but it is a byproduct of triglycerides. You know, everybody knows what triglycerides are, right? They're lipids. Okay? Cholesterol, triglyceride. When you reach my age, you'll know what triglycerides are, because that's what they always want to holler at you at. Okay? So in general, fatty acids, I'm going to put in parentheses, are lipids. So by definition, lipids are non-polar. Okay? So if it's non-polar, it is known as a hydrophobic tail. Okay? Alright, so what does hydrophobic mean?
Water heater.
It means it's a water hater or a fear of water. So it doesn't mix with water. So from here to here, our cell membrane doesn't like water. Okay? So, would it be a good idea for our cells to be this shape? No, it wouldn't, because what's our plasma made mostly of? Water. So we'd have a freaking hard problem, right? Okay? So we never want, always know that the tails go to the inside and the heads are on the outside, because they do come in contact with water all the time. Okay? This ability, having this and this, is what makes a membrane semi-permeable. Okay? Now, the problem is lipid to phosphate ratio. Okay? We'd like for it to be like it should be, like normal. Okay? So in other words, 52% protein, 40% lipid, 8% carbohydrate, which is what these guys end up being. Alright? So, let's say that my lipid gets increased. Alright? The cholesterol is the lipid that we're dealing with. Okay? Cholesterol can be unesterified or esterified. Okay? Okay, give me a second, I'll tell you. Alright? Unesterified means non-reactive. and this is reactive, okay? So little information you guys probably don't know at this point. Most hormones that we have in our body, so things like testosterone, estrogen, especially the sterols, the steroids, they're called sterols, we'll talk about that in chemistry, come from cholesterol. Cholesterol molecule gets esterified, so in other words, enzymatically changed to become active so that it can then transform into estrogen, testosterone, and lots of other hormones that we have in our body. Unesterified means that it hasn't been modified yet, so it's not ready to react with anything. Does that make sense? See? And essentially, you guys, esters are chemicals that can be used. All right, if you've ever taken, and I know some of you probably haven't, probably most of you haven't, an organic chemistry class where you're dealing with just organic compounds and stuff, things like methane and propane and all those organic alcohols, those kind of things. You'll see the word ester a lot of times. Ester just means that it's active. It's an activated compound, so it can interact with other things and cause problems or action or whatever. Okay, so we'll talk about those a little bit later on. All right. So our membrane, okay, also has these lipids. Also play a role in antigen production. Okay. So sometimes, based off of their protein content and other things that are there, this is where you get receptors and antigens in the cell membrane. So that becomes really, really important. Because remember earlier we talked about transferrin and EPO receptors. Okay, those are modifications in this membrane that receive those cytokines for us. Okay. So very important that this can be modified to make antigens. All right. How many people in here know your blood type? Okay. How many O's do we have? 2. How many A's? Okay. B, C, G, D. A, B, O, right? That's what we have. We have A, B, and O. And then we have A, B people, okay? So when we talk about our blood types, and you guys will talk a lot about this summer in immunology, Ms. Cole actually introduces blood bank that you'll take in the fall in the summer. Because blood bank is essentially, it's known as immunohematology is what it's called. We call it blood bank, but it's immunohematology, which is basically dealing with antigens, okay? So people who are A have a modified protein or antigen that is known as the A antigen, and it is on their red cells, okay? People who are B have the same, except it's different, but it's known as the B antigen, okay? People who are AB, they actually have 2. They have an A and a B antigen on their red blood cells. People who are O, we don't have either one, okay? We don't have that antigen, so we're 0. The O is actually 0 instead of the letter O. It stands for 0. We have 0 antigens, okay? Yes?
Well, then how do you have positive and negative?
Give me a minute, okay? Then we also have another protein that is known as the D antigen, okay? We have a whole system of antigens that are known as the RH. It stands for Reese system, and it came from the Reese monkey. That's how we discovered it.
Is that like RH positive and RH? I'm
That's
RH
it.
positive. What's
Okay.
that mean?
So that means that if you're RH positive, you're D antigen positive. You have it on your red cells. If you're RH negative, you don't have it. You don't have that protein there. So people who are like O negative, which is the universal donor, they can give blood to anybody. They don't have neither the A or the B antigen, but they also don't have that D antigen. Okay? Now, I'm going to muddy the water a little bit. Okay? We think about the D antigen Because what do we know? We know positive or negative, right? That's what we think of when we do our blood type. But there's actually a C, a little c, a big E, a little e, there's an F, a CW, and then there's like 3 or 4 more. There's like a bunch, okay, that are in this Re system that if you have them, they will all correspond to little proteins that are located on the membrane, okay? Now listen, yeah, I know you're like, damn, that's hard. This is just the RH system. There's a Kale system, a Duffy system, a Kidd system, M and N system, an S system, a P system, a Lutheran system, and a Lewis system that we mess with. And then there's all these other random rare ones out there also. Okay? So blood bank is hard in the fall. Okay? But listen to me, let me just go ahead and throw this out there to you. I don't care if you learn hematology real well and you're a hematology expert. I don't care if you're a micro expert. I don't care if you're a urinalysis expert. But when you get into blood bank, you better damn pay attention, because this is where we kill people in the lab. These little suckers, these little proteins, cause lots of problems in a lab, and they can kill you quickly if we don't do the right thing, do what we're supposed to do. So study extra hard in blood bank when we get there next fall, okay? Does that make sense?
You do?
Ms. Cole teaches it. I teach chemistry. I teach clinical chemistry. So next, in the fall, you guys will take clinical chemistry and blood bank, which are probably 2 of the hardest classes together. I hate it, but that's the way it is, okay? But anyway, so membrane, very, very important, okay? All right, so it can also alter the function and lead to cell death if you don't have the exact composition that you need for this membrane, okay? So 95% of the lipid content of the RBC membrane consists of unesterified cholesterol and those phospholipids. And then the remaining lipids are the fatty acids. Remember, think about triglycerides. And then glycolipids. Glycolipids are basically lipids attached to a glucose molecule. So they're called glycolipids, all right? That's where that carbohydrate, see where it says 8% carbohydrate? That's where the carbohydrate's coming from. It's a glucose molecule that's attached to a lipid, okay? So now, when we're synthesizing RBCs, sometimes things can go wrong in the production. And so if we've got an accumulation of things like cholesterol or triglycerides or anything else that is lipid, then it can mess up our red blood cell, okay? So we talked a little bit about the phospholipid bilayer, but I want to talk about things that can be a problem with it, okay? Every one of us in here have an enzyme, okay? There is an enzyme in our body that is known as LCAT, lecithin cholesterol acyl transferase, okay? Now this is probably one of the first enzymes that we've really talked about in the MLT program. You guys have talked about some enzymes in microbiology. So y'all talked about oxidase, right? Beta-lactamase. Remember those that for micro, okay? Anytime you see ASE on the end of a word, that is an enzyme. And remember, enzymes are just special proteins that catalyze chemical reactions, okay? So in this case, it is a reaction with a protein called lecithin cholesterol, and it says it's a transferase. So what it's doing is essentially changing an unesterified cholesterol molecule to make it esterified. Does that make sense? Remember what I told you? The difference between unesterified and esterified? Okay? So it's basically activating it. Alright? So once esterified, cholesterol cannot return to the RBC membrane. Alright? So if LCAT changes it to an esterified form, it can't be reincorporated into the membrane. And that's a problem. Okay? Because we do need that cholesterol because of that percentage of lipids that we need. So when this happens, it changes the shape of the red cells. Okay? Now, there is a abnormality or a genetic mutation where LCAT is not present in these patients, okay? So when they do this, they have free plasma cholesterol increases, and then it basically gets accumulation within the RBC membrane. And so what happens is leads to an expansion of the molecules, okay? So what you do is you get a special cell known as a macrocodocyte, okay? A codocyte, now listen to me. The last class was really confused about this. Every time they saw a target cell, they started calling it a macrocodocyte, okay? Listen to me. Codocyte is the science term for a target cell. Macro just means it's large, okay? So you can have codocytes that are not necessarily large. They're just normal size cells, but they're codocytes because of their membrane. All right? So a codocyte is known as a target cell. What's a target look like?
Circle.
A circle?
Circles.
Okay, right? Red cells are circles, aren't they? Okay? We have a central pallor, right? All red cells have a little central pallor, right?
What's a power?
You remember I told you guys how red cells, if you look at them like this, they're biconcave. You remember we talked about there's not enough hemoglobin right here to pick up the stain? So you get a central pallor. So you get an area that's white in the middle of the red cell. You got a red cell right in front of you? See that? That's the central pallor. Every normal red cell has that, okay? But if you look at that red cell, target cells have this.
I want to see a picture.
I'm fixing to put one up there, girl. Hey, hold your damn horses.
I don't have any.
Is there not none on the picture?
No, I don't know.
So not pictures in the PowerPoint? Yes, right there. This is a codocyte. Okay? So instead of it having the central pallor, it actually, and the reason it does that is because it kind of gets this shape. Because of an increase in lipids. Okay? So if you looked at it like this, it would look like this instead of this from the side. So the central pallor disappears because you get an increase here and here, but then you get a decrease here and here. Does that make sense? So it kind of looks like that. And so when it fills out, this is solid. Let me take that out now if I can. And you get a light pattern where there's no staining in this area. And so it gives it a bullseye shape, known as a target cell. Okay? So what causes that? Well, what causes it, look, you've got an inner and an outer. Okay? So, in this case, right, this is our membrane. And if it continues on around, this is the inside of the red cell. Correct? And then this would be plasma. Right? So this is the inner, let's say inner red cell, inner RBC, inside, right? This is your membrane, okay? So going around, and if we pull this out, that's what our membrane would look like, right? So everything here down is known as inner, and everything out here would be outer. That would be where your plasma's at, right? Okay? So when you have an increase, all right, target cells, though, because of the membrane, the increase in it. But we're going to talk about two more cells in just a second that have to do with this inner and outer. Any questions about a target cell? You see why it's called a target cell? Okay? Anybody know what that cell is? A broken one. Technically, it is a broken cell. This is a sickle cell. Okay? Have you ever heard the term sickle cell? Okay? Sickle cell is an ethnic disorder, all right, usually African Americans. That's the prominence of sickle cell. Instead of them making most adults make a hemoglobin called hemoglobin A, all right? A lot of times it's referred to A1, all right? But most of the time we just take the 1 off. That's your normal hemoglobin, okay? Every one of us, you don't have sickle cell, do you, Jordan? Okay. Every one of us in here, if we looked at our red blood cells, we have hemoglobin A, okay? That should make up like 98% of the hemoglobin in our body, in our red cell, okay? People that have sickle cell, they have an abnormality. So they have a hemoglobin called hemoglobin S, okay? Acts good, does what it's supposed to do until something happens and their O2 drops, their oxygen level drops. They get pneumonia, they get a bad cold, whatever, and they're not getting the oxygen they need for their body to do what it needs to do. As soon as that does that, a red cell that's normal, the hemoglobin that's normal, it becomes like a thick milkshake. Instead of being a liquid form, it turns into a milkshake and gets really, really thick and kind of polymerizes, is what we call it, okay? And when it does that, it sucks the membrane of the red cell and you get sickle shaped. Do y'all know what a sickle is? Have you ever heard that term? The Grim Reaper guy, you know, they used a sickle to cut hay with back in the day, okay? So it is sickle shaped, all right? Listen, we got a whole unit on, it's called hemoglobinopathies, and we'll talk about that in a little while, okay? But what I'm saying is, people who have sickle cell, they have an increase in target cells. Target cells go hand in hand with hemoglobinopathies. My point is, when we talk about the lipid problem, it's a macro target cell. It's large. Macrocodocyte. Okay? Codocyte is the term for just target cells, though. Okay? You can have normal sized target cells. Okay? But when we talk about that lipid problem, they're large target cells. Okay? All right? So, an increase in cholesterol ratio can cause us a problem, okay? It results in acanthocytes, okay? Acanthocytes. Decrease in the membrane fluidity leads to acanthocytes, okay? Acanthocytes occur when the phospholipid cholesterol ratio gets increased, okay? So you have the target cells, okay? And the target cells here, let me say this, there's not a change in the ratio, okay? There's just more cholesterol that is unesterified, okay? Still have the same amount. So in other words, the cholesterol level went up, phospholipid layer went up, the phospholipids, okay? But if you have a increase in the ratio, so that means an increase in cholesterol, but either stays normal phospholipids or even decreases, then that ratio gets messed up. Does that make sense? So this leads to what's called acanthocytes. Okay? Acanthocytes are fragments. All right? They're little fragments of RBCs. They're known as acanthocytes. Right there. So these are normal red cells. You've got some target cells here, so we know there's a problem with the cholesterol when we start seeing weird target cells and those kind of things. But now, when we see these, we also know that the phospholipid cholesterol ratio is off. Okay? One way or the other. Doesn't really matter. They're still going to form acanthocytes. Acanthocytes sometimes are also called fragments. RBC fragments. All right, you might see that somewhere on your list. Yes?
Does do they eat them and take them all?
The macrophages?
Yeah.
Yes. When they come through the spleen, they'll usually get destroyed. That is correct. But for a little while, they'll stay in circulation because of a membrane problem. All right, questions about that? All right, so now let's talk about those leaflets, okay? So the inner leaflet, okay, so expansion of the outer leaflet relative to the inner. So what we're saying is, if something happens and we get a lot of cholesterol that pushes out on here, then we form what are called echinocytes, all right? So my biology people, what does echino mean? There's a whole class of organisms called echinocytes, echinoderms. Remember, you know what those are? Those are sponges, starfish. What do they all have in common?
Spores. Spores.
Not spores, but something similar. They have spines. Okay? In other words, they're prickly, right? So echinocytes, their membrane looks like this. They're also referred to as Burr cells sometimes. Echinocytes or Burr. B-U-R-R. Burr cells. Okay, so then if it's the opposite, and you have expansion of the inner leaflet relative to the outer leaflet, you get an invagination. So this time, instead of this being here, it's over here. I lost my heads in my phospholipids. Okay? So you have an increase in lipids in this part, so it pushes out like this on the inner lipid, or inner layer. So then you get red cells that have this weird slot in the middle of them. Okay? And they look just like this. These are called stomatocytes. Okay? I've also saw them called slot cells. Alright? Like the slot of a coin. You put a coin in it. Okay? But theoretically, scientifically, they're called stomatocyte. Yeah? How many plant people do I have? Okay? So plants, the leaves of plants, have these weird cells that are kind of shaped like, well, that's not a good one, kind of shaped like this, that are openings. Guess what these are called? They're called stomas, or stomata, stomatas, okay, or stomas, okay? What they do is they allow water to go in and out. So like if you ever see the transpiration, the fog above trees, that means the stomata are opened and they're allowing water to go out because they've got too much in them. On a dry day, if you went to the desert and did a cross section of a desert of a cactus, their little stomata would be really, really tiny and closed, as tight as they could be. Okay? So these cells are called stomatocytes. All right? And it has to do with that inner and outer leaflet. Okay? So the edges of the bicuspid. Okay? Invagination, anytime you see the word invagination, it means to pull inward. Okay? That's what invagination means. It moves inward. Okay? I'm going to be really vulgar, but I'm not meaning to be. It looks like a vagina. Okay? That's the reason the vagina is actually called that, is because it kind of has that inward look to it. Okay? So it's called invagination. All right? And this is a picture of these cells. What?
What were you saying about a bicup something? What was that word?
Bicuspid. I didn't say anything about a bicuspid, did I?
Bicup or
You did say the word bicuspid, but
yeah, I don't
I
know.
don't know what you were
I don't remember saying bicuspid. I may have.
I
Said,
before the vagina thing. You were walking back and were saying something about bicuspid.
I
I'll
don't.
just listen to her.
Yeah, listen, because I don't remember saying it. I really don't. Because I don't know why I would say bicuspid. I really don't know why I would use that term.
Okay.
Sorry. If I did, I didn't mean to. Okay. All right. So echinocytes basically look like Burr cells. So you can see these guys got little spicules on them. These are Burr cells. Burr cells are really common in people that have that high cholesterol, and so that outer leaflet has got lots of cholesterol bound into it, so it's pushing it out. And also burn victims. People who have burns, like really, really severe burns in like a burn ward, they tend to have this, and it has to do with the hydration of the body, okay? So you'll see these echinocytes or Burr cells. They're also called Burr cells. And then these are stomatocytes, okay? And they look like little slots, okay? And sometimes they're referred to as slot cells. But in theory, they're called stomatocytes, okay? Stomatocytes. And if I ask you on test, I want stomatocyte, okay? Not slot cell. Okay, questions? All right, here's a good illustration, kind of shows you what we're talking about with the inner and outer layers and the extra cholesterol in those. So that kind of shows you that. That's pretty much all I really want to talk about for that thing. We've already talked a lot about the biochemistry of the RBC, metabolic pathways. This is what I was talking about earlier. We do anaerobic glycolysis. I kind of got ahead of myself. I knew it was in here, so I knew we'd eventually get to it. But at that point, it seemed a good place to stick it. And you need to know that. Doesn't have it. I think it's Embden-Meyer pathway, or Embden Embden-Meyerhoff pathway, I think is what it's called now, instead of the citric acid Krebs cycle. Okay. This is just an explanation of the pathways that you need to know. Embden-Meyerhoff pathway. I just didn't have it spelled exactly right there. See, Embden-Meyerhoff pathway. And I think in biology, this was always known as the Krebs cycle, is what we called it, the Krebs cycle. But this is what it's referred to as now. Okay. One of the things I do need to make mention of before we get any further in this is increased osmotic fragility. That's a big deal. We'll talk about G6PD deficiency eventually. We might not talk about it right now, but we will. G6PD is a glucose 6-phosphate dehydrogenase. It's another enzyme that's necessary for part of the hexomonophosphate shunt. So in your little chart here, right here where it says hexose monophosphate shunt, okay, glucose 6-phosphate dehydrogenase, G6PD. There is an abnormality people can have where they have a decrease in G6PD, and it leads to unusual, basically it's like, what's the term? Denaturation or denaturization. Denaturation is how you say it. In other words, breakdown of hemoglobin. It's been denatured. Hemoglobin's been denatured. And they call it Heinz bodies. Okay? Heinz bodies. And it's in the PowerPoint here. We may not get to it today. If we don't, that's perfectly fine. So all this is just talking about the metabolism inside. So just kind of be familiar that, remember, it's anaerobic. It still requires glucose. You still have to do glycolysis. And then this is at different points. Here's what we're talking about, the G6PD deficiency. So G6PD is necessary to turn it into NADPH, which is used to basically make ATP. And so we get that instead of like pyruvate. Okay. So the increase in G6P, or the decrease in G6PD gives us an increase in oxidative chemicals. Okay. And so when you have reduced levels, oxidation occurs really, really bad. So therefore, you end up getting denatured and precipitated hemoglobin. And this is those Heinz bodies that I was talking about. Okay. And this is important because this happens sometimes, and they're inside the red cell. So if these things are inside the red cell, and they're basically just big dots of hemoglobin that has been denatured, like this. So as that red cell is going through the spleen, the spleen sees those things inside and it starts taking them, trying to take them out. Okay? So you end up getting what we call helmet cells. Like that. And they look like they've been bit. And so a lot of people, instead of calling it a helmet cell, they'll call it a bite cell. Because it looks like those granules have been bit out of it. Okay? So that's an indicator.
What cell is that?
It's
Not
a
the
bite
Heinz
cell
body?
or a helmet cell. Yes.
It's a Heinz body.
No. The Heinz bodies are inside it.
Oh,
But once it gets to the spleen senses those Heinz bodies, and then it tries to grab them out as
Okay.
macrophages. Because there's nothing else wrong with the cell itself, it just senses that inclusion's in there. And so then it tries to jerk it out, and so you end up with cells that are known as bite cells. Okay? Heinz bodies, you can't see them on a right stain, you have to use new methylene blue. Okay? You have to use a super vital stain. New methylene blue is the one that's usually used. Okay? This is what Heinz bodies look like. Okay? Those are little Heinz bodies. So as those cells are going through, the macrophages sense that that's not supposed to be there. And so it reaches out and tries to jerk them out, and that leads us to a bite cell. Okay? All right, so we're not going to spend any time on this. The kinetics just means numbers. Okay? Usually kinetics is the motion and the numbers of cells. So this is like normal ranges at birth, adulthood, as you get older, and those kind of things. And guess what? We've talked about this already, over and over. So go ahead and look at this on your own and make sure you know what it's talking about. Okay? And I think, let me see, hang on. Yeah, we've talked about all this. Talked about EPO, all those kind of things. So I think that's pretty much it for... Okay, no it's not. This is important. So, Monday we'll start talking about erythrocyte destruction and then move on into the next chapter, or the next section. So probably what I'm going to do, instead of going to hemoglobin, I'm going to go to chapter 10 next. And then we'll come back to chapter 6 and get hemoglobin after we talk about the CBC. Okay? And then we can start doing more in the lab. Once we get the CBC under our belt and kind of know what's going on with the CBC, then we can go into more details. Okay? But we do need to talk about erythrocyte destruction, so we will talk about that on Monday. Okay? Questions about anything, guys?